Hello, all my JavaScript friends. This is TheVirtuoid, aka Mike Smith, and this is our RPG role-playing game. We're in the middle of creating a character sheet, which if you are following along on the code, not from the videos yet, because we got these videos scheduled out, you'll notice that it's getting rather complicated, but it's very essential that we have all those complications so that we can make this the best system possible. But one of the things that I did notice that I was not originally going to include within this RPG game was that what would happen if you had to do some sort of saving throw. And I'm using saving throw as an example here, but it's all over the place. And you may have, let's say, for death or poison a 12, but you get a bonus, a bonus of 2 or a -1 if you happen to drink some sort of potion or something like that. I don't know. But I needed a way to be able to do like a 3d6 plus 1, a 3d6 minus 1, maybe a 1d10 plus 12 or something like that. Whatever. I needed to have some sort of way to do equations. And so I had originally not planned to do equations, but I decided, let's go ahead and throw it in there because I want to be able to type in 3d6 plus 1 and have it give me a number. Or maybe 3d6 plus 2 times 7. And it gives me a number. Well, why that, I don't know. I'm just throwing examples out here. So today we're going to take a look at my equation class. So first of all, what we're going to do is let's go to the code itself. Well, actually, we're going to go through the design. The design is going to be very simple. It's going to be a static class, and it just has one static method called solve. And you pass to it a string. What do these strings look like? Well, the strings look like this. You want to say 1 plus 1 or 3 times 1 plus 2. That will basically give you the 9 automatically there. Or something as very complicated as this, which will include dice rolls. So not only do we have numbers here, but we can also include dice rolls within the equations. And so not only does this equation system will have to be able to handle all these different strings, but also have to handle all these different incorrect equations and be able to throw exceptions at that point. So the idea here, and I'm going to go through very quickly how it's going to really work. But the idea here is that we really have two basic types of data here. We have what's called an operand and an operator. And an operand is, if you take a look at the very first equation here, that 1 plus 1, an operand is an actual number. So it's either the number or the dice roll or something like that. That's all it is. The operator is the action that occurs, whether it's a plus, a minus, exponentiation, some sort of parentheses, something to that effect, or something along this line here, really complicated. We got 1, 2, 3, 4, 5, 6 operands, and 1, 2, 3, 4, 5, 6, 7, 8, 9 operators. So basically the idea here is that we're going to tokenize, first of all, this equation we put in here so that we can better work with them to know, hey, this is an operand. Hey, this is an operator. This is a left parentheses or right parentheses. Hey, this is a dice roll or something like that. And that will allow us to be able to then figure out figure out what that final number is going to be. But before we do that, let me explain to you very quickly how we're going to solve this issue. Basically, we're going to use a double stack method. We're going to have one stack that will be operators and another stack that will be operands. And the idea here is that as we find an operator within the equation, we're going to go to the operator stack. And if there's nothing on there, we're just going to push the operator. But we're going to compare that operator to the precedence of an operator that might be there before. And if we need to make a calculation, we will then take that operator, 2 operands or 2 numbers, and then make the calculation on its own, and then push that final number back to the operand stack, and then continue processing. Let's take a quick look at an example of how that works. Let's just take a very simple example, 1 plus 1, which you all know is going to be 2. So the idea here now is that when we tokenize it, we're going to have 3 tokens, a 1, a plus, and a second one. The first one is an operand, so it gets pushed to the operand stack. All just immediately gets pushed to the operand stack. The second token is a plus sign. So the plus sign will then go to the operator stack and say, do we have any other operators on there? Well, no, we don't. Well, I'm just going to push myself to the operator stack, and we're done. So that's it. Then the third token is going to be a 1. That gets pushed to the operand stack automatically. Then we are now done with the equation, and so we do what we call a reduce stack. And the reduce stack basically says, okay, we're going to take everything that's on the stack and we're going to keep reducing it down until we have all the numbers that, or the final number that we need to end up with. How does that work? Well, we first take we pop off the first operator off, which in this case happens to be a plus sign. And then we take two operands, making very careful note of which is the first operand and which is the second operand. So if we now pop off those two operands, the first operand that we're going to do will be the first one that we had pushed on. The second operand will be the second one we pushed on. In this case, both of them are ones. So then we do the operation 1 plus 1. For instance, if we had 2 plus 1, it would be 2 plus 1. If we had 3 plus 1, it would be 3 plus 1, and so on and so forth. But 1 plus 1 is equal to 2. We have now popped off that operator. We popped off those two operands. We put the 2 back on the operand stack, and we reduce again. Well, we don't have anything left on the operator stack. So we now take a look at the operator stack. It should be empty. It's empty. Great. There should only be one number and one number only on the operand stack. There is number 2. Therefore, we have a correct solution to the number 2. And this works for everything. But how about precedence? Because as you know, if we take something, like 1 plus 2 times 3, for example, you know that multiplication, you do multiplication first before you do addition and subtraction, which means we're going to take the 2 times the 3 and multiply those together first, which gives us 6. Then we're going to do the 1 plus 6, which will give us 7. How does that work? Well, first of all, we're going to have 5 tokens, the 1, the plus, the 2, the multiplication, and the 3. So we push the number 1, great. We take the plus sign and we go to the operator stack, say, hey, any operators on there? Nope. Okay, we just push it on there. Great. Next, we push the number 2. Next is the multiplication sign. Multiplication sign says, are there any operators? Oh, there is. Oh, okay, check that last operator. On that last operator, if the precedence of the incoming operator, which in this case is multiplication, is greater than the precedence of the operator that's on there, which is positive, then we push the operator, a multiplication sign. If the operators were the same or less than, we would reduce it at that point. So if we had 1 plus 2 plus 3, at this point the plus would be coming in. They're the same precedence, so therefore we would add 1 plus 2 to get us our 3 first, and then plus 3 will get us to 6 eventually. But it's not. It's a multiplication symbol. So now on our operator stack, we're going to have the minus sign and the multiplication symbol. Well, on our on the operator side, we're going to have the plus sign and the multiplication symbol. On the operand side, we're going to have the 1 and the 2. So our 5th token comes in as 3. It's an operand, so we push it to 3, and we're done. We reduce the stack, multiplication. All right, that's going to take the second one on the list, which will be 2, multiply by the third one on the list, which is 3. We're going to pop those things, multiply them, get a 6, push that back to operand stack. So now we have a plus sign on the operator stack and a 1 and a 6 on the operand stack. So the plus sign takes that. We take the 2, 1 plus 6 equal to 7. We push that on the operand stack. We're done. No more operators, 1 operand. It's a legal and valid equation, and we get 7. And this works with parentheses. This works with multiplication tables, multiplication, division. It works with everything. Let's show you how you can very easily control the amount of operators and the operands and the precedence that they do. So now that we've gotten all that, let's take a look at the code. All right. The code itself is relatively simple. All we have to do is, there's our static solve. All we're going to do here is we're going to tokenize it and then parse out the tokens. Tokenization is very, very easy, but I do want to show you one thing. The tokenization system is basically we get ourselves a little pattern, a little regex pattern to be able to get all the different matches, and then we go through each one of the matches. If the match ends up being an invalid token, didn't have the number D, it didn't have a dice or anything like that in it, we throw an exception there. Otherwise, we push that token after classifying it. And what do we mean by classifying it? Classification basically means that it's going to be either a dice, which case we're going to return, it's going to be an operand, which it's either going to be a dice, which we're going to return a value. Then the dice has the number of counts and the number of sides, which all dice need. It's either going to be an operator, in which case we pass over what the operator is and its precedence. Precedence is extraordinarily important. or we're just going to pass a number in this particular case. In this case, the value is going to be parse float. So each one of these has a type and a value. And so once all that happens, we get ourselves an array. Now, one thing I do want to tell you, because I always want to be upfront with you, what is all of this commented code out here? I left it here on purpose. Well, that is my original way of doing the parsing of the tokens, or the tokenization of the system. This is the way that I was taught how to tokenize strings way back in the 1980s. And I'm being very serious about this. That's the way I was taught. That's the way I was taught. That's the way I was going to do it. And it worked great until I tried to implement the dice section. And once I tried to implement the dice, it literally was getting ready to be a huge conglomerate mess to be able to do it that way. So I thought there had to be a better way of doing it. Well, regex, regular expressions, are available in JavaScript. So I asked AI to help me with it, and AI gave me this, which was wonderful, and it worked like a champ. So again, I'm just being upfront with you. I have AI do a lot of my unit tests because unit tests are not fun and they're tedious. I very rarely have AI do any kind of coding for me, but sometimes you need it when you don't know what to do, and I have no knowledge of regular expression. So again, just being upfront with you, AI did do this one for me. So there we are. That's the way it is. But anyway, we got our tokens. Like for instance, the 1 + 1, we now have 3 tokens, a 1, a plus, and a 3. And we're going to parse out the tokens. Parsing out the tokens is very simple. We're just going to go through a little for each loop here. We're going to basically figure, first of all, let's get through. If it's a number, we're just going to push it to the operand. And if it's a dice, we're going to get the dice value and we're going to push it to the operand. And if the dice value is incorrect, it's going to throw an error at that point. So I don't test for whether the counts and the sides are correct. The dice will do it for me automatically. The big thing here is the tokens, the operators. The big thing, the first of the big thing here is that if the operand's length is 0, like if there are no operands whatsoever on the system, then we know we're at the very beginning of the equation. And what I want to do here is that if we are not a plus sign, a minus sign, or a left parentheses, we're going to throw an error. And if we are a minus sign or a plus sign or a left parentheses, then we're going to push values onto the operands and operator stacks. If it's a negative value, we're going to push -1 and an operand. We're going to push -1 and an operator of multiplication. Same thing that we're going to do here for the plus sign. We do that on purpose and be able to keep people from doing stupid things like that. And if it's just a an open parentheses, then we just do this. Else, we do have operands on there. All we're really wanting to do here is that we're going to basically, if it is not a left greater than sign, we're going to do the reduced token stack. And that's where I said when we do the reduced token stack, we're going to sit there and say, okay, we're going to now take our operator and do the actual calculations. Otherwise, this is really no big deal here. Once we're finished with the tokens, we reduce it one more time because we make sure to get that one operand. If there are any operators left, we throw an error. If there's more than one operand left, we got an error. Reduced token stack is very, very, not really very simple, but the real key here, more than anything else, is that what we want to do is that we want to be able to tell the system here that when we've got an operator on there, and when we got an operator on there and our precedence is correct, the big thing we want to do here is we want to be able to then do the calculations. And here's what's very important. Remember, the first value of the equation 1 + 1 or 1 + 2, for example, it got pushed first. The 1 got pushed before the 2 got pushed. So it's very important that we keep the operand 1 and operand 2 separately, because especially for division, if you did 1 divided by 2, you don't want to say 2 divided by 1. So you want to be able to say 1 divided by 2, and this will keep everything nice and even and keep everything nice and even and legal. And so it's very simple here. Oh, here's our addition. Here's our subtraction. Here's our multiplication. Here's our division. And of course, we don't do a division by 0. And here's our exponentiation. And so that's pretty much all there really is to the reduce token stack. The key here is to be able to reduce the token stack when we need to reduce it, to be able to push the operator onto the stack if we need to, which we always do pretty much, and to reduce it one more time at the very end of the equation. And once we do all that, we just return the final value, because the final value is operands of 0. And that's it. And it works like a champ. How do we know that it works like a champ? Well, let's bring up the test. In our test section here, I've got a bunch of different valid equations that I'm using. And basically, this is kind of a copy of those valid equations. See, like the big one right there. This is a copy of the valid equations and the invalid ones from here. Here are all my valid ones. Here are all my invalid equations. And so all we have to do is test them. So let's take a look at that testing section, which I already have up on the screen. Let me just bring that up on the screen so that you can see it. There we go. So here you can see we've got all our simple equations. Here are all our different complex equations. And here are all of our invalid equations. Now notice there's 3 of them that were missing. Should solve with multiple implied multiplications. Should solve parentheses with implied multiplications. That is the one thing I have not gotten yet. Let's take a look at the code. And I want to show you why I've done that. Let's go to the design. The implied multiplication here is an equation that looks like this. 3 parentheses 1 plus 2. There's an implied 3 times parentheses 1 plus 2 there. I don't solve for that yet because I decided, no, let's force everybody to be very, very exact with their equation. And that will allow me basically to, later on, we may implement that, but this allows me to be to make sure that my equations are correct and that there's no flakiness going along. So that's the only thing that I don't have implemented yet are these implied multiplication rules. But other than that, that's all there is to our equation class. Thanks for watching. Subscribe to this channel to view more videos. Click on the like button on this video and visit us at TheVirtuoid.com. Also, support us on Patreon, where you can get access to member-only videos. Links are down below. Again, thank you very much for watching, and keep on coding.